I am Ganesh and I work at TU University. And today I am here to explain the scheduling problem which we came up with, which we believe would be able to address the title on the slide. And I'll be discussing the extensive simulations which we conducted on the scheduling problem. So we know that data centers consume a large portion of energy. The estimate for 2030, which you see on screen, is somewhere between 900 to 2000 terawatt hours. Now, this energy requirement also includes the inefficient energy consumption within the data center, some of them which is inevitable because they are taken by the support system like lighting, cooling. But there is also another part of this inefficient energy which does not provide any form of meaningful output, say the idle times. So for our scheduling problem, we believe that load maximization problem would help us to reduce the existing idle times. Again, and the study by how actually study the trend of AI training jobs and the additional electricity consumption which they bring along with them, and it's predicted to rise in future. But these jobs being not interactive provides us a little bit of flexibility. So we would like to give a commitment, but after introducing a small slack into the system, so we introduce deadlines. Now, our scheduling problem looks something like this. We have parallel identical machines where we do not have any form of preemption, and we have jobs with deadlines. The algorithm which we use to build our problem has two components, one being the acceptance component and other being the allocation component. The acceptance component which we try are greedy and threshold. Greedy, as the name suggests, deals with the job as they come. So we have the first come first serve basis. You take the job, you check whether this can be finished in time or not. If not, you reject it. The threshold, on the other hand, compares the deadline of the new incoming job with a parameter known as deadline threshold. And if the deadline is smaller than this threshold, it rejects, else it accepts the job. Now, the allocation policies which we try are load balancing, where we allocate the new job. If accepted, we allocate it to the machine which has the least load. A form of bias loading, where once we accept the job, we look for the machine which is the most loaded and which can finish the job before the deadline. The third allocation policy would be minimization of idle times. What this does is when you schedule a job on a machine, if it has multiple cores, then it might end up blocking a few cores and the idle time accumulates. What this algorithm does is it tries to minimize the idle times which are formed on these cores. And finally, we also try backfilling variant of the load balancing and bias loading policies. The second portion of our work is the workload generation. We use existing cloud traces, but the data in these traces are not enough for our simulation. So we generate deadlines statistically, we add it to the existing workload, and then we run extensive simulations. The whole set of simulations which we ran was more than 2 months, and we have all our results on our web page. Let me start by explaining what greedy acceptance with bias allocation is. We'll name this algorithm as greedy best fit. So whenever we have a job coming up, we update the remaining cores for all the remaining load on all the machines. And now you look at the least loaded machine, check whether the job can be accepted or not. If the job can be accepted, then you move up to the machines which are more loaded than this, And you finally reach a point where you have the most loaded machine on which you can fit this job and finish this before time, and one step above it, you can't. So you pick this scope, you put the job, you schedule the job on this machine, and you are done. If the job is not, if you are not able to schedule the job on even the least loaded machine, then you simply reject it. I'll explain this with the help of figures, where I also explain the other two algorithms. If you look at the center allocation over here, this represents the greedy best fit, which we just discussed. And before I explain the details, let me just quickly say what the colors represent. The gray part on this graph represent the already existing load on the machines. The blue part over here is a new incoming job. Say, this is the load profile of the system as of now, and we have a new job coming in, which is released at point 3, and which requires 2 time steps and 2 cores for its execution, which has a deadline of 11. Now, what greedy best fit does is it looks whether the job is schedulable on the least loaded machine. Yes, it is, but that is not sufficient. Now it goes through the cores which are more loaded than this and checks which is the most loaded core where it can schedule the job. Greedy balance, on the other hand, simply accepts a job and schedules it on the least loaded one. Now there's one more color which is in these diagrams. What this represents is the idle time created by this new job on the system. So the third variant of min idle, what it does is once the greedy method accepts the job, it moves the job through all the cores, looks for the least idle time, and then uses this particular core or machine for scheduling this particular job. Now, I'll explain the backfilling variants which we used in tandem with greedy balanced and greedy best fit. If you remember from the previous allocation of that job, this is how the load profile in the system looks like. Now, over here we have an idle time of 4. Over here we had an idle time of 3. If a new job comes in, we first move through all these holes. We check whether we have enough space to schedule the job. If so, we do it. Else, we move ahead with greedy balance or greedy best fit like the previous one. Finally, I would like to explain the last algorithm, which is the threshold algorithm. Now, this algorithm was published by Jamalabadi et al. And this provided near to optimal optimal results for very small slacks. How this algorithm works is for every job, it updates the course, then it determines the deadline threshold. How this deadline threshold is determined is it takes every individual machine has its own threshold value, and deadline threshold is nothing but the maximum of these threshold values. How do they calculate this threshold? That's based on a function value which they arrive at using a recursive formula. So once you have the deadline threshold, you check, you compare it with the incoming job deadline. If the deadline of this job is less than the deadline threshold, they reject it, or they accept the job and they allocate it based on greedy best fit, which is biased loading method. Now, one thing which we have to know is threshold may reject the job which greedy might have accepted. Now, I talk a bit about the workload generation. We take the base data from the Google cluster, and of the given of available data, we are interested in the 4 specific data. One is the time point at which the job is started. The second, the time pointed with job is halted. Third, the unique identifier. And fourth, the unique identifier of each subtask. How this helps us is we have to remember that these trace files also include preemptive data. So a job with a unique identifier name will have multiple start and stop points. We consider the first instance of appearance as its submission time. Then we add up all the pieces of the job together and we consider this as the total processing time of the job. We count the number of subtasks which are associated with each job to be the total number of core requirement for the job. Of the given trace, we split the jobs into days based on the time limit of 86,400 seconds. And if we split it further into based on different time limits, we get the following job population. The gray area are very high jobs, jobs of very high length. These are distributed throughout, but we found that they have a large number of jobs we submitted on the first day. And the blue area are the jobs which are less than 60 seconds. For our study, we considered these jobs over here, which are greater than 60 seconds and less than a day of length. We split the jobs further based on their core requirements. And this is how the number of jobs looks like. For example, these are the single core jobs, the core with limit of 30, with limit of 120, 5,000, more than 5,000. And how we arrived at the total load is we multiplied job length by the number of cores taken by the job, and then we had this particular graph over here. Now we come to the part where we generate the deadline. We use this particular slack condition for generating the deadlines, and for each slack we use log normal distribution with following steps, and for each slack we have a range of standard deviations which we use. So we will end up with 99 files for a single day. Now this itself will not be enough. In order to remove any further biases, we generate 10 such different sets and we average out the results. Since threshold theoretically was optimal for very low slacks, we also use a special data file with a slack of 0.01 and standard deviation which is half of it. Before I explain about the simulations, I would like to explain a bit about the performance ratio. Now, we arrive at the performance ratio by using the formula total load processed in an optimal scenario by total load processed by the algorithm. This part over here should be straightforward to understand. I would like to explain what total load processed in an optimal scenario means. For that, let us consider a small scheduling scenario where we have 3 jobs which are submitted in the order 1, 2, and 3. Now we have 2 machines available for 4 time units. The greedy acceptance, it accepts job 1 and 2, rejects job 3. But in an optimal scenario, we could have processed job 2 and 3 and rejected job 1. So in this case, the total load processed would be number of cores or number of machines into the total time steps for which the machines were available. If we look at the 3-core scenario, then we end up accepting all the jobs. We still have 2 slots, but we don't have any other jobs left. So in this case, the total load processed would be the summation of total submitted jobs. When we use this in our simulations, we use the minimum of either number of cores or machines into the make span of the schedule or the total submitted processing time which we have. Now we have implemented the algorithms in Java and simulated using Eclipse. For like I mentioned before, for each Slack, we have generated 10 sets of data, and for each Slack, we have 11 standard deviation combo, and Slack itself, we have 0.1 to 0.9, and we have 10 sets. For each day, we have 990 sets of data files, which we need to run simulations on. We have also considered scenarios where we have this limited number of cores. So what this means is one core scenario includes only those jobs which require one core for execution. The 30-core scenario contains all the jobs which require cores between 1 and 30 with the limit, and all other jobs which have requirement greater than 30 are omitted. For 120, we do the same, but with the cutoff of 120 cores. And for 5,000 cores, we conduct experiments for pre-selected days. We also conduct experiments with backfilling, but it's only for a particular Slack. Now, let me try to explain the results which I'm displaying over here. So let me start by explaining the maximum load. If you remember the performance ratio equation, this is what it represents the numerator. Over here, the value of number of machines into make span is lower. So we take this particular value, and at a particular point, this term exceeds the total processing time of the submitted jobs which we have. So from here on, we have the total submitted jobs, the processing time of the total submitted jobs. These results over here represent the performance of each algorithm with respect to what we have. The vertical lines over here represent the various results or the range of results we got for each set of a particular Slack standard deviation combo. In this case, it's 0.8 and 0.8 by 2.5. From now on, we only represent the average values of these results. So if you look to the right, we have results for 3 different days for the same Slack standard deviation combo. We can see that the algorithms, they follow a general trend over here. So from this point onwards, we'll show results for a single day, but with changes in the parameters. We have a single core results for day 11 for various Slacks. We have very small Slack of 0.1, a medium Slack of 0.5, and the large Slack of 0.9. Over here, we can see that for very small Slack, there's literally no difference between the balanced and the best fit allocation, with load balancing and bias allocation perform similarly. However, the threshold is performing really worse. But as the Slack improves, we can see the difference in performance of load balancing and bias loading becomes more and more significant. But the threshold algorithm, it moves towards the greedy best fit. So if you remember, all our algorithms had 2 different components, the acceptance component and the allocation component. What we observed was the acceptance component of threshold algorithm. As the Slack value increases, the number of machines which contribute to determining the deadline threshold, they go on decreasing. So as a result, more jobs get accepted, and the allocation part of this component is same as greedy best fit. So this is why we observe this trend of this particular algorithm converging towards the greedy best fit. We also show you the heat maps. Before explaining the heat map, I have to tell you what value we have used for plotting the heat maps. We have calculated the performance ratio of greedy balanced and greedy best fit. And we have taken the difference between these two values and we have tried to plot it across the range of standard deviations. As we can see, we have some vertical structures over here, which means over the range of standard deviations for a particular main slack value, there isn't much of a difference, but the difference between the performance is significant when the slack value itself changes. To check whether the threshold algorithm is performing better for a much lower slack, we generated a special set of data. But over here also we see that threshold is not able to perform any better. Now, I would like to discuss the results for 30 cores. Over here, we do not consider threshold anymore since the study was for a single machine, single core, but we include greedy min idle, which tries to minimize the idle times. Now, for really small slack, we see there's no significant difference, but the trend between the balance and bias loading, it continues the same as that we saw in the single core jobs, but min idle seems to perform similarly to that of greedy best fit. We confirm this with the heat maps, and the heat maps actually represent the difference between balanced and best fit. We can see similar vertical structures, and as the slack increases, the difference becomes much more significant. Now, we look at the results of cores with a cutoff of 120. For very small slacks, it doesn't matter, but as it increases, the greedy min idle starts to perform better than greedy best fit. But please remember that this machine, this algorithm has to check each and every possible machine on which the job can be scheduled before it can allocate the job. So it comes with an increased computational effort. Now we have the backfilling results. We can see both greedy, balanced, and best fit with backfilling perform better than the non-backfilling variant. However, the hierarchy of performance continues with backfilling as well. Greedy min idle does perform better than greedy balanced with backfilling, but greedy best fit with backfill is still the best algorithm in the lot. For highly parallel workload with 5,000 cores, we are not able to find any particular clear differentiation between the performances of the algorithms. So this is the result which we had. So we can see over here we have some kind of vertical structure, but it's not. In previous cases, we had this repeated on other days as well, but over here, we are not able to see such clear differentiation between the performances. So coming to conclusion of our study, we are seeing that for small slack values, the acceptance method is dominant when you compare it with the allocation method. But as the slack value increases, we can see that the allocation one actually gets better because we see the threshold algorithm which moves down. Now for moderate number of cores, in our case we had 30 and 120 cores, we can clearly say that a bias loading actually outperforms load balancing. Even the minimizing idle times and backfilling variants, even if they perform better, they come with comparatively large computational cost. So these were our observations from the experiments which we ran. that brings it to the end of my presentation. Thank you for your attention. And if you have any questions, please feel free to ask.
Thank you. Questions?
I do have a question. At the beginning, you explained a little bit the meaning of the performance ratio.
Right.
I have to say I have a bit of a struggle understanding what it really means.
You mean?
So how do you achieve the optimal scenario? What do you consider the optimal scenario again?
Yes, the values which we use for obtaining this optimal scenario are two. We always take the minimum of the two values which we have. One value is we have the make span of the schedule, and then we multiply this make span with the number of machines or cores which we have. So we have a rectangular region which we say we have this many resources which are available with us, but we are still rejecting the jobs. The other case is where we have enough resources, but we don't have enough submitted jobs. So we add up the processing time of all these jobs, and we always take the minimum from these two values. And this is the reason why you see this curve over here, because with low number of machines, we have this make span, but we have lot of jobs which are being rejected. At one point, the value which is dominating this min criteria changes and it flattens out.
I see. Okay. Thank you. That's my question. Thank you.
We still have 3 minutes, so if anyone else has a question. So this system is designed for some edge computing applications. Did I get it correctly?
Not exactly. What we are trying to do is we are trying to put in constraints on the number of cores. So we are not considering the very large parallel jobs or very large cores system. We have these constraints, and we are trying to see how these algorithms perform under these specific constraints.
I see.
So we don't have highly parallel jobs. We actually include some parallel jobs, but not really large ones.
Yes, yeah, so, but the renewable power source means that the system is intended to operate, like, I mean, on its own, off the grid, or
yes, but then you have the limiting to this number of cores which you can have in such a system.
Mm-hmm.
And this is exactly what we are trying to do. Not use a very large setup, but we are trying to restrict the number, and we are checking how the jobs should work on such a system.
Yeah, because in one figure, in one figure there were like 3,000, 5,000 cores, which doesn't seem.
This was for very large ones. We just wanted to see whether the results hold when we have very large cores, whether we are able to find a distinction between the two algorithms. So that's why we have it at the end. All other ones, we have stopped in 120. And now we wanted to check whether the results which we have for this course hold as well. So yeah.
Yeah, thanks. Yeah, I got it. Okay, thank you very much.
No problem.
Can I ask one more thing?
Yeah.
Was the system where you were testing this actually powered with renewable power sources?
Which one?
Was the system where we were testing this
Oh.
actually powered with renewable power sources?
No, this was a simulation.
Okay.